Hello, everybody. Welcome back. Today, we're going to be talking about oxidations, reductions, and nucleophilic acyl substitution. And so, at this point in the course, now that we are past exam two, the way that this part is going to kind of go is it's actually going to be much faster than the previous parts of the course because previously we were building our knowledge. That way, we were able to then apply it to reactions. This is the point in the course that we have now hit where we are no longer building any primarily fundamental knowledge, and instead we are now applying that knowledge to a bunch of reactions, which means that we're going to be hit with a lot of different reactivities, and everything should still be based on the same rules that we talked about before. And so in today's lecture, we're going to be covering what feels like more material than we have been across the last couple of weeks, but in reality, it is going to be all based on those fundamentals. That way, it shouldn't be too difficult. And so for today's lecture, we're going to start by actually focusing on the nucleophilic acyl substitution side. And so this is all to do with these functional groups called carbonyls, right? And so carbonyls, I'm sure you are aware at this point, is any carbon oxygen double bond with any substituent off of it, right? That is essentially what this is. And so with these carbonyls, they can do some really interesting chemistry. And to give you an idea of what these carbonyls can do, and it's called this nucleophilic acyl substitution, essentially, let's say we took this right here, which if you all know your functional groups, this is an acyl chloride, right? And this acyl chloride, if we were to take this and toss it into a solution of sodium hydroxide, right? Let's just say that it were in excess for the sake of it, um, in water. And then we're going to need a little second thing where we use some HCl and H2O, but we're going to talk about what that is in a second. Normally, if I were to give you this as a question, you may think to yourself, what's going to happen? Because we do clearly have a strong nucleophile around here, strong nucleophile slash strong base. But looking at this acyl chloride, we know that this right here is sp2 hybridized, and normally we can't do this type of chemistry on an sp2 hybridized carbon, right? We wouldn't normally be able to do SN2. But funny enough, this reaction does yield a carboxylic acid, right? Which is another one of those functional groups that you need to be aware of. So if this yields a carboxylic acid, it's very clear that somehow, some way, this is actually adding in there and doing a substitution. The question is, how does it happen? Well, if we're looking at this acyl chloride and we think about carbonyls in general, right? Carbonyls are a little special because we've talked about this a little bit beforehand. They actually have an established dipole, where the oxygen up here has a large amount of partial negative charge, and the carbon has a large amount of partial positive charge. And previously, we had related this to the fact that there's a resonance form that you can draw that is not the major resonance contributor, but it still ends up giving us a negative charge on the oxygen, a positive charge on the carbon. And what this is essentially saying for us is this resonance form right here is where the reaction actually occurs, right? Just like all other types of resonance, resonance here actually defines our carbonyl reactivity. And this is going to be a trend you're going to see with carbonyls, right? They have this partial positive charge that's pretty good. And so you can imagine in this resonance form, if our hydroxide is around, right? Because the sodium's just being a spectator, it doesn't matter. It can come in here and it can add into that carbon. Upon doing so, what we end up generating now is a really funky looking structure, right? We've added in our OH from our hydroxide. We still have that oxygen with a negative charge, like was shown in that resonance form. We have a chlorine right there. All right. Normally, though, this step is shown in a single manner, right? The resonance that is right here is shown along with the adding in, right? So most of the time, if people are drawing this, what they'll do is they'll have shown the carbonyl, they'll have shown the hydroxide, and the hydroxide actually adds in and then the electrons also go up to the oxygen all at the same time. And the reason is that is more likely what is occurring in terms of energy. Because remember that resonance form is not energetically favorable because it's creating charges when there don't need to be any. But this single addition that is forming and breaking a bond is much more favorable. Now then, that being said, let's return to this idea that we have created, this very interesting structure. Well, essentially, sitting in this structure, we have an oxygen with a negative charge, and then what we have that's a little more important is we have this chlorine right here. And this chlorine, we know, is a good leaving group, right? And it would be nicer if that had the negative charge in comparison to the oxygen. So you can think of this as if you were to try and do something with this, it looks more tertiary, so you couldn't really do an SN2, but the chlorine could leave on its own. But because that would leave a carbocation, and that's not really a good thing, the oxygen actually forms a double bond to assist in kicking the chlorine off. And the main reason for this is because now you've eliminated the charge on the oxygen by giving it a double bond. The OH is still on there, and you've kicked out Cl minus, right? Which was a great leaving group, and it is very stable. So what we've gone from is a relatively unstable hydroxide to a very stable chloride. And the thing is, this isn't where it stops because I already said that the NaOH was in excess. You can imagine we've created what is now a carboxylic acid, right? And in the word, it says acid. The reason for that is if you remember back to acid-base chemistry, this thing has a pKa of right around 5. So if it's hanging out in a solution that has more hydroxide, then very clearly the hydroxide will deprotonate the carboxylic acid, leaving us with the negatively charged conjugate base, which is a carboxylate, right? And that has, of course, generated some water, which is just the solvent. Now then, from here, this is officially the end of the reaction, right? That would be the end of step one here. And then step two, this HCl H2O, this is what we call a workup step. And you're going to be seeing a lot of these around because these workup steps essentially are going to take what is a relatively unstable and hard to isolate ion, and it's going to turn it into something that's actually isolatable, right? So in the case of taking this and adding in HCl and water, I'm sure that you can tell that HCl being a strong acid will protonate that negative charge, and so you'll end up with the actual carboxylic acid. Now you may be thinking to yourself, the whole point of that last step doesn't make much sense. But let's draw an energy diagram to see what's actually occurring here. So in this energy diagram, right, we have our reaction progress still on the X here and energy on the Y. From our starting reactants, right, the first addition is a substitution, or a, I guess, addition nucleophilic. And so it's going to have a relatively high activation energy. And you'll notice that our first intermediate is not much lower in energy, right? It's essentially going from what is an OH minus to this other still negatively charged oxygen. But you may be thinking to yourself, well, why is it slightly lower? Well, essentially the enthalpy here is relatively favorable, and this negatively charged oxygen is actually stabilized by induction from the other groups that are attached to that carbon. And so it's a very slight stabilization here because it's also slightly disfavored by entropy. So this first step doesn't have much going for it. And the second step, though, we know that by doing that intramolecular reaction to kick out the chloride, that's a very good and stable thing to do. But then even more so, following this is that step that actually does the acid-base chemistry, right? So if we were labeling this on the x-axis, the last step is our ABC, which we can see is exothermic, right? Because we're going from something with a essentially more unstable base to a more stable conjugate base. We're going from the O minus to the O minus with resonance. And we've talked about many times before why that's favorable. We see that the leaving group expulsion, right? So kicking it out is favorable. And then the addition from the original step is relatively barely favorable. So overall, the acid base there in that last step being favorable actually does push it towards a lower energy product. But then once you do the quenching step, you can imagine that you would go to what is essentially I2. So this is where you land after quenching. And quenching, of course, is that workup step that we just talked about. So this is the entire basis of this idea of nucleophilic acyl substitution. You're starting from some carbonyl compound, you're kicking out a leaving group, and then you are forming something that's more stable, right? So essentially, with nucleophilic acyl substitution, that does mean that we need two important things, right? The first thing we would need is that we need a nucleophile to add to a carbonyl, right? That nucleophile has to be relatively unstable because, again, it's all about the stable uh, leaving group that we're kicking out. The second thing is we need a good, and we're going to put that in quotes, leaving group to be ejected, and a new carbonyl will be formed, right? Because notice that we started out with a carbon-oxygen double bond. The only thing we really did was replace the chlorine with the OH because we reformed that double bond at one point. So with that being said, we can think about this in a very simplistic way, right? We can do a general idea where we have some leaving group X plus some nucleophile with a negative charge, forming a carbonyl with some nucleophile attached with the ejection of X with a negative charge. And you can imagine that just like I was talking about above, equilibrium direction relies on what the identity of the nucleophile and X is. Right? So it entirely depends on these. So, thinking about that, we can go ahead and we can look at some functional groups and what types of leaving groups they should have. Right? So, we're just going to create a little chart here on the next page of functional groups, a structure, and then what should be the leaving group from that structure. So, the first one is going to be these acyl halides. Right? And these are pretty good because you can imagine every structure is going to have some type of leaving group already attached to it. And of course, that could be Cl minus. We could also draw it with a bromine to make it Br minus, or an iodine, we can make it I minus. These are all really good leaving groups, right? So generally speaking, these are pretty good to kick out, right? The next thing we can think about is, all right, if we were to look through the functional group worksheet for some other carbon-oxygen double bond containing functional groups that are carbonyls, one of them that we'd find is an aldehyde, right? Thinking of an aldehyde, that group over there is a hydrogen. So if we were to think about what the leaving group would be, it would be H minus. Now, I don't know about you, but H minus does not look very pleasant. As a matter of fact, it is a super terrible leaving group. Right? And we know this because when we think about this as a base as it is, it's not very stable, right? It ends up giving us a pKa of the conjugate acid of about 35. So it is incredibly high energy. We don't really want to kick that out, especially whenever we think about it in terms of this statement up here where the nucleophile would have to be strong enough to warrant us kicking that out. All right, the same thing goes for another type of carbonyl derivative that we can talk about, which is called a ketone, right? You may recognize this one as well from your functional group worksheet, because this one, if we were to kick out anything, it would have to end up being something like a CH3 or some type of carbon-containing atom. Now, that being said, if you look at this here, carbon with a negative charge is also a terrible leaving group. So the thing is, you're not going to kick that out either. General rule of thumb for things like this, right? And this is going to be very important for later on. You never really want to break carbon-carbon or carbon-hydrogen bonds if the hydrogen is a leaving group. Because remember, they can act as protons, right? So general rule of thumb, CH3 minus and H minus will never be leaving groups. The bond is just too strong. Now then, moving a little bit down the line, there is a functional group that is, and I don't believe on your handout, and that is called an anhydride. And what an anhydride is it's actually two carbonyls that are side by side. But you can imagine, in the case of this trying to do something by kicking out a leaving group, if you kicked out a leaving group from one of the carbonyls, it would actually be a carboxylate, right? And so this would be an oxygen with a negative charge that's stabilized by another oxygen through resonance. So this is actually a decent leaving group, right? It is somewhat stable. Now, that being said, again, it also still depends on the nucleophile. We'll take a look at that in just a second. But then there's two other functional groups that are on your functional group worksheet. Those are esters, right? So an ester contains a oxygen leaving group, but this one would, of course, have just a negatively charged oxygen. And that's not usually a very good leaving group based on what we talked about previously with SN2. But keep this one in mind because it has something interesting going for it. And then last but not least, we have something like an amide, right? And of course, amides have nitrogens as their side chain. And so if we were to use something on an amide as a leaving group, it would be a negatively charged nitrogen. This is in the same field of also very bad leaving group, right? You really never want to kick out negatively charged nitrogens because remember that these are also incredibly basic, and the conjugate acid has a pKa of about 35. So this is also a terrible leaving group. All right. Now, just as a little sidelight, because I'm sure that this will come up in some of your questions that you may think of, carboxylic acids are another type of carbonyl, right? Because we've seen them all around. And you can imagine that if we were to break this bond, it would form OH minus. But the thing is, this usually does acid-base chemistry first with strong nucleophiles. So in reality, we really don't have to make that argument because it's probably not going to be substituted. Okay? So let's go back to this little statement that we made about the ester. Right? I said that the oxygen that we kick out just has a negative charge, but I didn't say it was really bad. The question is why? Well, let's take a look at a reaction that we could do with an ester that would actually be favorable. And as a matter of fact, it's the same one we did with the acyl halide, right? If we added in an excess of sodium hydroxide and water, and in this case, we technically don't need to add in excess, but I'm going to show it anyway, and then we quench with HCl and water, what we'll end up seeing is that we'll actually make a carboxylic acid and methanol, right? But how is this possible? Because it's very clear that normally O minus is a bad leaving group. Well, if we take a look at the mechanism, it's going to become slightly clearer, right? First step that we're going to see is the same as what we saw with the acyl halide. The hydroxide can add in and push those electrons up to the carbonyl or oxygen. So remember that this is just that resonance and addition shown in a single step. That's going to give us our attachment to the OH. And now we have the negatively charged oxygen on that side. And now look at what happens. Let's say that we did decide to kick out the oxygen with the methyl as our leaving group. Well, you can imagine that at this point, we have not changed much in terms of our actual stability. We went from an OH minus to a OCH3 minus. Now then, that would actually be just a pretty much perfect equilibrium between the two. But the one thing that is very important about this is the carboxylic acid differs quite a bit from the ester because of the final step of this reaction. It has an acidic proton, and that acidic proton can be deprotonated by the methanol or the methoxide that we just kicked off, and that will generate a carboxylate along with methanol. All right. And then from here, of course, by taking this and adding in the HCl and H2O, you're going to get your appropriate carboxylic acid after workup. But that step right there, this acid-base chemistry, this is the reason this is favorable, right? Let's look at it in terms of energy. So in terms of energy, if we were to draw one of our classic energy diagrams, the reactants are going to start up here at whoops, sorry. Our reactants are going to start up here at a relatively decent energy. And upon addition, we're going to end up going up to some intermediate. And you'll notice here that unlike with the acyl halide, this is actually slightly endothermic. Now, that might be slightly surprising, but remember that the induction from the chloride is actually more than that from the oxygen in this case, just because it's pulling away more electron density, and the carbonyl is more reactive, leading us to this slightly higher energy state. But that's not the important one because the next thing that happens is when we kick out that methoxy, we end up at the second intermediate, right? At the second intermediate, your energy is pretty much the exact same as reactants, right? The same can be said about I1 as well. It would be very similar if it wasn't due to entropy, so another thing to keep in mind. But then from here, from I2, once the acid-base reaction occurs, it plummets because that acid-base is super favorable. So in reality, when we're looking at this reaction, our delta G here has a massive benefit from the acid-base chemistry that occurs there at the end. That's the only thing that really makes this reaction favorable. All right. So when thinking about this idea, this big benefit that we get in terms of that delta G, it would kind of feel like, okay, well, if that's the case, then shouldn't we be able to do this with just about every single one of these, right? And the answer to that is not really, because let's say we took a look at something like an amide, right? Because we already said that doing the amide's a bad idea. Well, let's look at why. Essentially, if we were to take this and run it under the same conditions that we have these others, excess sodium hydroxide and water, and then try and do that HCl in water, we would see no reaction, right? It is just not possible. Question is why? Well, if we take a look at what would happen in the mechanism, essentially it starts out the same as the others, right? Hydroxide would come in, it would do its nucleophilic attack on the carbonyl carbon, right? Kick the electrons from the double bond onto the oxygen, and we would end up in a situation like this. From here, we now have a choice, right? Because if these electrons were to come back down and form a double bond, the question becomes, what is the leaving group? And the thing is, if you think about this nitrogen right here, it will never be the leaving group, right? Because the OH that we have that's right here will be kicked out as an O minus. And that is versus what would be the N minus. So in terms of energy, this oxygen will always be favored over the nitrogen, right? So essentially what we're seeing is if we were looking at our energy graph, the transition state energy to get from I1 to I2 would be drastically higher, and I2 would also be drastically higher in energy because essentially we would be trying to kick out something that's more unstable than what we started with. So even though we would end up with that massive benefit from acid-base chemistry if it were able to happen, we're never going to be able to get over that energy hump. So amides you cannot kick out in this way. And it essentially brings up this really important level of reactivity. And I'm going to call it flowing downstream, right? Because we can think of it as kind of like a river, right? Where based on what group you have to start with, you're going to end up with a different group at the end, right? Because you can start out from something like an acyl halide, right? So an acyl halide we've talked about is a really good reagent to use in these types of reactions because it has that really good leaving group. If you use the acyl halide, you could, if you wanted to, transform it into an anhydride, right? The leaving group on the acyl halide is so good, you could kick it out with something like the carboxylate. From there, you could then turn this into something like an ester, right? That is very possible. And then the ester could flow downstream even more to make something like an amide or a carboxylic acid. But the thing is, the river only flows one way, right? So this is our river of nucleophilic acyl substitutions. It only flows downstream this way. All right. What that's telling us is that just based on the energy of these systems, you can always go from something on the left towards something on the right, but you can never do the reverse. Okay? So, say we wanted to take something like an anhydride and we wanted to make it into an ester. How would we do that? Well, we would add a strong nucleophile oxygen with an alkyl chain on it. Right? So something like that ethoxide and ethanol, you would go from an anhydride, you would do the addition to the carbonyl, and then you would kick out the leaving group, which we know is this big chunk over here, right? That is our leaving group. Essentially, we would end up making an ethyl ester, right? And that is good for the river's flow, right? This is an appropriate way to go. It's energetically favorable. Let's say we wanted to go from something like an acid halide over towards an amide, right? How would we do that? Well, we would add in a nucleophile that's relatively strong. In this case, we could actually just do a normal amine because remember that neutral nitrogens are still strong in DMF. But you will sometimes have to deprotonate those neutral nitrogens, by the way, to make these reactions work energetically. But essentially, you can go from your acyl chloride to your amide doing this, right? You just kick out that chlorine. This is another good direction. That is the correct way the river flows. But say you wanted to try and do this by going from something like an amide to something like an acyl halide, right? You couldn't add in something like NaCl and expect it to go in this direction, right? The river only flows one way. So essentially, this reaction here is just not possible energetically. All right? So whenever you see these types of reactions for nucleophilic acyl substitutions, it's always going to be flowing from the left down towards the end of the stream on the right. So that being said, there are some other applications of nucleophilic acyl substitution, right? So we're going to call this a interesting little piece that's not normal as to what we're talking about, but it is going to be useful for us here in the future. So, one thing that you may have seen on a couple practice worksheets is there are some reactions where there are alcohols and they're being mixed with something that looks like this. And now you may recognize this a little bit from what we've talked about beforehand. It looks a lot like a tosyl group. And this, as a matter of fact, is called tosyl chloride, TSCl. And this is actually how you make tosylate leaving groups. You do use this reagent with triethylamine and DCM. And you can imagine what we're looking at here is the chloride is a good leaving group. And then this area right over here with the sulfur oxygen double bond, it looks like a carbonyl. And you'd be absolutely correct to assume that. Because if we look at what's going to happen in this reaction through the reaction mechanism, what you'd see is that the alcohol is actually going to go ahead and act as a weak nucleophile, but it's still good enough to come in here and attack the sulfur, right? And this generates an intermediate where the sulfur now has an oxygen with a negative charge. It has the double bond to an oxygen, it has a chloride, and it has that aromatic ring still attached. At this point, we look over and we see the chloride is ready to act as a leaving group, and so the oxygen gladly obliges and lets it leave while forming the double bond back and kicking it out. Once this happens, we now have the oxygen that we originally used as our nucleophile positively charged, and then we have that sulfur with everything hanging off of it over there. From here, we do have in solution triethylamine, right? That NET3, which is just a weak base that's there to come in, grab that proton, and actually generate the neutral oxygen so that now it is a happy tosylate. Oops. So essentially, this reaction is a nucleophilic acyl substitution. But the entire point is now you've generated this group right here, which we know from previous works is the tosyl group. So we've now made this an OTS leaving group from doing the nucleophilic acyl substitution, right? So this is now a good leaving group, whereas the alcohol that we originally had was not. All right. So essentially, you can use nucleophilic acyl substitution to lead into other reactions because from here, of course, as a primary leaving group, this would be really well set up for something like an SN2. All right, let's move on to our second important thing that we're going to talk about today, and that is oxidations and reductions. So oxidations and reductions are pretty important reactions because so far we've talked about two really important functional groups that come from oxygen, right? Those are alcohols and carbonyls. And you'll notice the main difference between alcohols and carbonyls is that there is a double bond there. The other thing that you should notice is if you were to do a quick count of these, you would find that the alcohol, in this case, has total valence electrons equal to 26, right? That just comes from counting the two electrons in each bond as well as the lone pairs around it. And then you'll see that the total valence electron count over here for the carbonyl is actually 24 electrons. And now you may be thinking back to Gen Chem and thinking this is going to be a really terrible time because, oxidations and reductions get very confusing sometimes. But this is going to be very, very simple for organic chemistry, right? The difference in these two is that double bond in the middle, and it's the fact that these are also redox partners, right? They are redox from one another. Where to go from an alcohol to a carbonyl, this is a loss of two electrons because it's going from 26 to 24. So this is technically an oxidation. Whereas the opposite direction, going from the carbonyl with 24 electrons to the alcohol with 26, this would be a reduction. And the reason that you should remember this is because of a classic thing you probably learned in Gen Chem, which is this little oil rig abbreviation, where the oil is oxidation is loss, right? And so, of course, that is of electrons. And then reduction is gain of electrons. And here in organic, we're going to actually focus quite a bit on this idea because oxidations and reductions allow us to swap between alcohols and carbonyls. But it is a lot less complicated than what we see in Gen Chem. But the first thing that we need to do before talking about oxidations and reductions is we need to learn how to calculate oxidation states, right? So oxidation states are a little important. They won't seem as important immediately, but they are very important for later. Essentially, the idea behind these is it tells us um, how different atoms are going to be acting in terms of how much electron density they truly have. So the way we calculate oxidation states is we have to make two assumptions as we do them. One is normally we talk about bonds as equally sharing electrons, right? And then sometimes we talk about them as having dipoles. But for this, we are going to assume the bonds are completely polarized. All right. And so what that means is essentially you're going to treat them as they are ionic. All right. One thing's going to have the negative, one thing's going to have the positive. So it is ionic like. The second thing we're then going to do is we are going to add the values from each bond to get the oxidation state. All right. So let's try this on something like methane, right? If we're thinking about methane, it's just CH4, right? But the thing is, we want to draw this as an oxidation state drawing, right? We want to figure out what the oxidation state of these things are. And the first thing that you need to do to know this is you need to look at your electronegativities because the electronegativities are going to tell you how the bonds are polarized. You're going to give the electrons to the atom that has the higher electronegativity because that would mean it wants it more, so it's going to take them in terms of acting as though these are ionic like. So if we take a look at the electronegativity of hydrogen versus the electronegativity of carbon, carbon, of course, has an electronegativity of 2.55, and then hydrogen 2.20. Right? And this shouldn't be super surprising for everyone because, of course, there is a reason that hydrogens are usually protons, and it's because they usually don't like to have electrons around them. And so if we were to convert this into an oxidation state drawing, right, and I only show these drawings as a useful way to see this, it's not necessarily the most scientific way to draw this, but it makes a little bit of sense. Where the carbon with those hydrogen bonds, we now are assuming that they are dissociated. And essentially, the hydrogen is getting the raw end of the deal where it has no electrons around it. So it's going to have a plus, whereas the carbon is going to have a negative for each bond because it is taking all the electrons from the bond. So then if we're going to calculate our oxidation states, we would say that the carbon oxidation state is equal to -4, right? Because there are four negative charges on the carbon. And then we would say that our hydrogen oxidation state is equal to +1, right? Because each hydrogen just has a plus and we count them all as separate. So we're going to say each hydrogen is in a +1 state. Okay? So essentially, you're just going to find the electronegativities, you're going to determine which bond goes which way, and then you're going to assign oxidation that way. So let's do it in a different one that's a little bit harder, where we have more things than just hydrogens, right? Let's say that we were looking at a structure where we have a carbon that has a methyl as well as an OH attached, and you may recognize this as ethanol. So, what does ethanol look like in terms of an oxidation state drawing? Well, first we need to check that electronegativity of oxygen. Hopefully everyone is well aware that oxygen is more electronegative than something like carbon. It does have an electronegativity of 3.44. So if we were looking at this specific bond, and keep in mind I'm going to only look at this specific carbon because the other one is not as important here. I just want to give better examples for all the oxidation state drawings that we're going to do. Essentially, the carbon-carbon bond here is actually not going to be polarized, right? Because they have the same electronegativity. So instead, we're going to draw that as a full bond because essentially this is neutral due to the same electronegativity. On the other hand, we can actually polarize these other bonds. So we know the carbon-hydrogen bond, the carbon is taking the negative, the hydrogens are taking the positive. On the oxygen-carbon bond, though, the oxygen takes the negative and the carbon takes the positive because oxygen is more electronegative. So if we look at this and we want to calculate oxidation state of the carbon, right, we would see that in this case it has two minuses, a plus and a neutral. So if you added all those together, you'd see that the carbon oxidation state is -1. So if you're thinking about this versus methane, like we had calculated beforehand, and you were asking yourself which carbon is more oxidized, you could say the carbon in methane is more oxidized because its oxidation state is lower. All right. Now, if we go back up to our original drawing of the alcohol and the carbonyl here, we can also check the oxidation states of these, right? So let me also write a title in here. So when we're thinking about our oxidation state of the carbons that the oxygen is connected to, right? Because the oxygen won't really change oxidation state much, but the carbon will. The carbon on this side is connected to two carbons, which is neutral, a hydrogen, which gives it a minus, and then the oxygen, which gives it a plus. So it is actually in an oxidation state of 0. Then on the other side, when we're looking at this carbonyl, now we've taken away the carbon-hydrogen bond to where there's now just carbon-carbon, carbon-carbon, and then two carbon-oxygen bonds. Each of those carbon-oxygen bonds is a plus for the carbon, so this carbon is in a +2 oxidation state. So this is another way that we can see that looking at these, we're going from a carbon that is more uh, the word I guess would be more reduced to a carbon that is more oxidized. Okay, so let's actually look at what oxidation is. I think I also misspoke earlier. I said that the carbon and methane was more oxidized. I meant less, right? The more positive, the more oxidized something is. All right, not the more negative. That was my fault. Okay, looking at this, let's look at actual oxidation of alcohols. So if we did want to do an oxidation, we actually already know how to, right? Surprisingly, whenever we talked about E1, we learned about eliminations, and eliminations are a form of oxidation, right? If you think about an elimination reaction, you'll always end up with 2 electrons less in your total molecule than you started with. So it is just a form of oxidation. Now, that being said, for alcohols, we have to do something a little bit funky. We have to take the alcohol and try and perform an elimination where something is going to have to be the leaving group. But clearly, the things we're getting rid of are hydrogens. So, how do we do that? And the answer is with a very fancy reaction using chromium. So, this is CrO3 with H2SO4. This is what we call the Jones reagent. And it is the primary useful thing that we're going to see that ends up doing oxidation of our alcohols. But here's the thing. We got to look at a mechanism on how this works because it's a little weird. right? The first thing that actually happens in this reaction is not one that we're going to know a mechanism for. You don't have to. You should be able to figure it out just by pushing arrows, but we're not going to focus on it in the class. It is actually that CrO3 alongside water and acid, right? So that's why we have the H2SO4 in water, will end up making this structure right here. And you'll notice it looks quite a bit like sulfuric acid, and that is because it is very similar. This is called chromic acid. All right, and chromic acid is the actual oxidant, right? So in this reaction, the true working reagent isn't shown there, but it's formed from these three coming together. So what does this chromic acid actually do for us? Well, essentially, the chromic acid is somewhat similar to a carbonyl, but what's going to happen with it is the acidic water that it's in is going to be strong enough to actually protonate the chromic acid and make it positively charged. At this point, what we've done is we've essentially created a situation where we're favoring the resonance form that puts the electrons on the oxygen, and it's kind of like a carbonyl, right? Because if you think about our carbonyls, right? Let's just do a little sidebar up here. Which one would have a more reactive carbon? One that just does a resonance form that puts a negative charge on oxygen and a positive charge on the carbon, or one that starts out with a positive charge on the oxygen, but its resonance form just puts a positive charge on the carbon and keeps it as a neutral oxygen. Clearly, the one on the bottom is going to be more reactive because there's more plus charge on the carbon, right? It's more positively charged. It's the same way here. We're putting technically more positive charge on the chromium because we can also draw that resonance form. And so what that means is our alcohol is now able to do a nucleophilic attack and kick the electrons from that double bond up to the oxygen. Upon doing so, we have now created what is essentially our reactive intermediate, where we have the chromium attached to our oxygen, and it has a bunch of alcohols now hanging off of it, right? This right here is not necessarily a good spot for our reaction to be in. What's going to happen is some water at this point is going to want to help get rid of that negative or that positive charge because it is incredibly acidic. It's going to actually deprotonate it. And then one other thing that I want you to notice here that we're not going to show is more of the chromium chemistry, right? Where the chromium's actually going to do some stuff and it's going to end up losing some water. All right. This right here is not shown in our mechanism because we don't have to know it. All right. I'm just going to make sure that this is relatively simplified for everyone. That way it's not too confusing. So from here, we have now generated a structure that ends up looking like this. Right, so keep in mind this is after the deprotonation and after the loss of water. I should actually make this a little nicer. So, at this point, what have we truly done? Well, we've actually generated the important intermediate of our reaction because this group right here is a good leaving group, which is exactly what we needed for this oxidation to occur because we needed a good leaving group that we could kick out for an elimination. So if this is ready for elimination, that just means that all we have to do is take the hydrogen from this position and deprotonate it. The question is, what's going to do that? An external base? Well, surprisingly, no. What's going to happen instead is an interesting set of arrows that we're going to see, where it's going to be the actual chromium reagent that grabs the proton. What this then does is it deprotonates it to form the alkene, and it also kicks out the chromium reagent all at the same time. So it's three arrows that are showing an elimination that is occurring through the chromium, or I guess the oxygen down there, as the base. This, of course, is going to kick out the ketone as your eliminated product alongside a chromium with three hydrogen or two hydrogens, three oxygens, and there's going to be a little bit of charge funniness going on in there. But this right here is just a byproduct that we don't worry about. All right, it'll do more fun chromium chemistry to essentially remake chromic acid later on. So, what's the moral of the story here? Essentially, the moral of the story is that it is just an E2, right? This mechanism right here is a single step elimination. It is practically an E2. All right. And that's what oxidation is. It's just an E2. Now, that being said, oxidation would be very, very simple if that's all we had to worry about, but there are a couple hang-ups that we have in this reaction. And one of those is with primary alcohols. So you notice we were using a secondary alcohol here, right? Because the carbon that it's on is secondary. So that's something to keep in mind. But what happens if the carbon that it's on is primary? Well, if we were to take our chromium reagent with H2SO4 and water, we would end up forming a carboxylic acid, which looking at that, it doesn't make much sense, right? How is it that we would remove a proton, do an elimination, and somehow form a carboxylic acid? And the answer is we do the elimination, but then something else weird happens. So essentially, you can think of it as from our alcohol, there will be some first step of oxidation, right? We could draw out the whole mechanism. We're not going to because it's the exact same one as we drew up there. And that is going to end up forming an aldehyde, right? Which would make sense because the aldehyde should be the functional group that's formed upon removal of the hydrogen and doing an elimination. But this aldehyde in this solution does not survive. Instead, a second oxidation event occurs that is aided by water. So the other oxygen that's in our carboxylic acid, because you can see if I were to pull out the highlighter, this oxygen right here is equivalent to that oxygen right there. But then we need another one to come in. Where does it come from? It comes from the water. So what that's telling us is that only if water is present will this second step actually occur. And the second step essentially occurs through the water adding in to the aldehyde, right? And not kicking out something as a leaving group, but instead staying around and doing a second oxidation. So, what this is essentially saying for us is that if we are ever working with a primary alcohol and we have water around, that's going to give us a carboxylic acid. Now, that being said, there is a way to not do this, right? So, preventing water is relatively easy. What we do is we just swap out the reagent that we're using. Because if we take a primary alcohol and we use what is called PCC in DCM, what'll happen is the PCC actually acts as our oxidant, right? And essentially, it's the same type of oxidant, just slightly different to make it actually work. It's still chromium. That's what the C actually stands for, the second one that is in PCC. You don't actually need to know what this is. All you need to know is that there's no water, which means there is no second oxidation. So in this case, we end up with the aldehyde. just because there's no water. So again, one of the things that I want you to be aware of as we go through these next lectures is that I'm not always going to be asking for mechanisms anymore. Some things you're just not going to have to worry about it. You're just going to have to know that it happens. Thing is, you can probably figure out the mechanisms on your own if you tried, but you don't have to. Okay? So just know that PCC, since it doesn't have water, will make an aldehyde. So with that being said, we have a nice little table that we can create with the alcohol type, right? So that one we're going to split into three different categories. We can do a primary alcohol, a secondary alcohol, or a tertiary alcohol. And then we're also going to take a look at these all under two different umbrellas. One where we would be using CrO3, H2SO4, and water. And then one where we would be using PCC, which is the one without water, and DCM. What we would see is essentially with primary alcohols, right? We already know the main difference between these, and that is that in the case of primaries, the PCC can't do a second oxidation, so it gets stuck at the aldehyde, whereas the chromate with H2SO4 and water, that Jones reagent, that one ends up forming the carboxylic acid. All right. On secondary alcohols, though, you may notice one important distinction between these is that it can't do a second oxidation. And the reason is because there's not a second hydrogen to do an elimination. Notice that the aldehyde has a hydrogen right here that can then do another elimination later on, but these don't. So actually on secondary alcohols, these two things do the same thing. They form the ketone, right? They both just do one oxidation because it's the only one they can do. And then finally on tertiaries, looking at these, we didn't go over these, but it's for a very simple reason. On this carbon, there's just other carbon bonds and the carbon-oxygen bonds. There's no hydrogen, which means there's no elimination, right? Because of that, it can't react. So on a tertiary alcohol, these reactions are not possible. They are no reaction. Okay? Just because it can't do the elimination. So realistically, when we're talking about the difference between the Jones reagent and PCC, we're primarily looking at what is going on in this column right here, the primaries, because the secondaries is all the same. Either way, what it all boils down to is that it does an oxidation that depends on the alcohol type, and you're going to end up with some type of carbonyl from your alcohol. Next time, we're going to go through and we're going to talk about the opposite direction of this, which is doing reductions. So we're going to ask ourselves, what happens if we try and take a carbonyl and return it to an alcohol? So I'll see you next time for that lecture, where we'll also talk a little bit about Grignard reactions. See you then.